It's a pleasure to have Brendan McKay, who is a professor at Australian National University. He gave a very interesting talk on our big seminar, and it's a pleasure to have him on this conference. Of course, it's a pity that it's only online, but hopefully in the future we'll do it physically. And Brendan will talk about degree sequences of random hypergraphs. Thank you, Brendan.
Well, thank you all for coming. This is joint work with Catherine Greenhill, Tomasz McCoy, and Mikhail Isaev. So you should know what a hypergraph is. An R-uniform hypergraph is one where all the edges of size R. So this is a 3-uniform hypergraph because every edge has 3 vertices. The degree of a vertex in a hypergraph is just the number of edges that contain that vertex. And the degree sequence, of course, is just a list of the degrees. So you can see there the degree sequence of that example. So the problem we're going to be considering is, suppose you take a random R-uniform hypergraph with n vertices and m edges. What is the distribution of the degree sequence? And just to be clear, we don't allow repeated edges. We could allow it, would be a similar sort of calculation, but we don't allow it for this calculation. And by random, I always mean uniformly random. So every hypergraph that's R-uniform and has n vertices and m edges will be equally likely to be chosen. I have to define a few variables. N is the number of vertices. M is the number of edges. R is the size of the edges, and all the edges are the same size. Nice bold red D is the degree sequence. That's a list of the degrees of the vertices. And little d is the average degree, just the average of the degrees of the vertices. So H sub R of D is defined to be the number of R-uniform hypergraphs with degree sequence D. P sub R of D is the probability that a random R-uniform hypergraph that's with n vertices and m edges has degree sequence D. Clearly, firstly, m is the sum of the degrees divided by R, because every edge contributes R to the sum. And from this, you can see that one condition, which I won't mention again, is that the sum of the degrees has to be a multiple of R. And you can also see that the number of hypergraphs with degree sequence D is just the total number of all hypergraphs multiplied by the probability that they've got degree D. So this double binomial thing here, n choose R is the number of sets of size R, and you're choosing m of them. So that's the total number of hypergraphs with R-uniform hypergraphs with n vertices and m edges. What's been done before, and of course when R equals 2, that's just the case of graphs, and that's been worked on extensively, and I'm not going to try to survey that. I'm only going to consider the case of edges of size at least 3. Dudek, Fries, Ryczynski, and Szielaikis counted the asymptotic, all of these are asymptotic counts. They did the fixed edge size and the degree being little o of square root of n. Blenovsky and Greenhill counted those hypergraphs where the maximum degree satisfies that equation there. So in the case of regular ones, this is a similar condition to Dudek, Fries, Ryczynski, and Szielaikis, but Blinovsky and Greenhill's result allows the edge size to increase as a function of the number of vertices and allows a variation of degrees. It's not only the regular ones, as long as it satisfies that inequality there. The result that's most similar in method to ours is a result of Kuperberg, Lovett, and Peled. They only did the case of regular hypergraphs. Regular, in case you didn't get already, is that every degree is the same. So the regular case is an important point in enumeration, but it doesn't tell you anything about the degree sequences of random ones. So a random one is extremely unlikely to be regular. But they did the regular case providing the hypergraph and its complement each have at least n to the c edges. And all they said was that there is some constant c, and they didn't tell us how to find it or what it is. So this is a little unsatisfactory because it means we can't apply this result for any fixed edge size. So if for edge size r, the number of edges is at most constant n to the r, and we don't know if r is big enough to be greater than this unspecified constant c. However, if r is increasing, it gives us non-trivial values for the number of regular hypergraphs. Finally, the most extensive work was fairly recent. It's not published yet, it's on the archive, by Kamchev, Liebenau, and Wormold. Firstly, they have some results for very sparse hypergraphs that cover the cases that I mentioned before, but I won't discuss those much because we're dealing with the more dense hypergraphs. So if the edge size is at most n to the 1/4 over log n, so the edge size is allowed to increase with the number of vertices, but not as fast as n to the 1/4. And the average degree increases faster than any power of log n, and it's less than constant over r times n minus 1, choose r minus 1. So that expression looks a bit mysterious until you realize that n minus 1, choose r minus 1 is the degree of the complete hypergraph, where every set of size r is an edge. So they've hit up to the density c over the edge size, where c is a sufficiently small constant. They also have a bound on the amount that the degrees can be different from each other, and this bound depends on the edge size. It's a little bit larger than n to the 1/2. It's a power of n greater than n to the, sorry, not n, d. It's a power of d greater than d to the 1/2, and that power depends on the edge size. And I won't give you the details of that. So let's look at our conditions. First of all, we'll note the problem has some symmetry that divides the space of edge size and degree sequence into 4 quadrants. So firstly, if you have a hypergraph, you can complement it. You just put in every edge that's not present and take out the ones that are present, same as taking the complement of a graph. And this has an easily determined effect on the degree sequence. So because of this, we might as well assume that we've got less than or equal to half the number of edges that the complete hypergraph has. Another thing you can do is you can complement each edge independently. So the edge W becomes V minus W, every vertex that's not in the edge. So you complement each edge, but you keep the number of edges the same. This changes the edge size from R to n minus R, and you can again work out what it does to the degree sequence. So because of this one, you might as well assume that the edge size is less than or equal to half n. And those two assumptions together define what I call the first quadrant. Of course, you can do both of these things at once. So you get 4 ranges that are all equivalent to each other. In the first quadrant, what our conditions are is, firstly, there's no condition at all on the edge size, except that we don't treat r equals 2 because that's been done before. As far as the average degree is concerned, we can go up to half of the complete graph. So that's no constraint at all. But on the lower side, we have to have at least r to the 4th n log n. And that sign there means we're increasing faster than r to the 4th n log n, average degree. We also have a condition that requires the degrees to not vary too much from each other. And this is a bit hard to explain, so I have to have an aside to explain it. Okay, so let's let V choose R denote the set of all R sets of vertices, and let beta be a vector beta 1 up to beta n to be a vector of real numbers. Now, for an R set W, define lambda sub W like that. It's exponential of the sum of the beta j over W divided by 1 plus the same exponential. You can see from looking at this that it's a real number in between 0 and 1, strictly between 0 and 1. And when you have a real number between 0 and 1 and you like probabilities, you think, oh, let's call that a probability. Let's construct a random R uniform hypergraph with each edge selected independently. So each R set W is present with probability lambda W. Now you choose beta so that the expected degree sequence is D. So the expected degree of vertex J is the sum over all the W that contain J of lambda W. So every edge that contains J contributes 1 to the degree of vertex J, and lambda W is the probability that edge W is present. So for each vertex, we'll set this expectation equal to the degree sequence we're interested in. These equations are called the beta equations. Then, of course, nonlinear equations, because you've got these exponentials in the definition. It's not immediately obvious that they have a solution. And this is something that's been studied. They usually do have a solution when you think they might. And if they have a solution, then the solution's unique. But if you find the solution to these equations, then what you have is the beta model of random hypergraph for parameters R and D. So this is a type of random hypergraph where each R set is independently present as an edge, but the probabilities are different for each such R set. And the average degree of each vertex is the DJ coming from the degree sequence that you're interested in. So this model of hypergraph has got many interesting properties. I'll just mention a couple of them. One interesting property is that the probability of a particular hypergraph occurring depends only on the degree sequence of that hypergraph. So any two hypergraphs with the same degree sequence have got equal probability of occurring. A second one is interesting to statisticians. So in statistics, one model that's considered is the hypergraph model, where every R set might occur with some unknown probability. And then what you observe in the population is the degree sequence. So then the question is, what edge probabilities should you infer from the observed degree sequence, or it could be average of a large number of degree sequences. And if you use the maximum likelihood sense of best fit, then the maximum likelihood set of edge probabilities is the probabilities that come from the beta model. You can discuss that more later if you wish, as a peripheral to our calculation. Not all of the analysis is the same as the analysis for other examples, such as the beta model for graphs. And one reason is that for hypergraphs, there's no equivalent of the Erdős-Galai inequalities that tell you when a integer sequence is the degree sequence of a graph. And in fact, the problem of determining whether a sequence of integers is the degree sequence of a hypergraph is NP hard. And it has lots of nasty properties like a polytope that's not convex and things like that. I won't go into that.
Brendan, sorry, can I ask a very quick question?
Yes, sure.
Is it NP hard even for R equals 3?
For R equals 3, it's NP hard.
Oh, okay. Thank you. Yeah. Very interesting.
I wouldn't have guessed that, but that's what's been proved. So now, in terms of the numbers beta, our requirement on the variation of the degrees is that the degrees are, the beta values are all the same within big O of 1 over R, R being the edge size as always. Notice that for the regular graph, for the regular hypergraphs, all the betas are the same. So this maximum would be 0. And as the degrees become different from each other, the betas become separate as well. And we want that the maximum difference is big O of 1 over R. This is not completely satisfactory as a theorem condition because the betas are the result of solving some nonlinear equations in n dimensions. So people want to know whether it actually applies in their circumstance. So fortunately, we can prove a lemma that says this condition on the betas holds, providing the degrees don't differ from the average degree by more than relatively constant over R, where the constant is sufficiently small. So if every degree is average degree times 1 plus or minus small constant over edge size, then the condition on the betas is satisfied. And this is probably fairly close to sharp. We do have some more versions of it that give some additional conditions, but it's fairly close to sharp. Okay, so how do we prove that? Well, you start off with the betas for the regular case where every vertex has got degree D, and then you follow the trajectory of steepest descent to solve these nonlinear equations. And with a bit of effort, you can find bounds on the determinant of the Jacobian of the equations, and that shows you that the trajectory doesn't stray too far away from the point you started. This is the shortest abbreviation of a long proof that you've seen, but that's it. So now, how do we do it? Firstly, we write the problem as a generating function problem. You consider this, we have a variable xj for each vertex j, and then we take the product over all R sets of 1 plus the product over the R set of xj. So this corresponds to the choice. The 1 is for not choosing W as an edge, and the product of the xj's in that edge corresponds to choosing that edge. Now, if you think of multiplying out this large product, what you get is a polynomial, and the degrees of the degree of xj in any term in this polynomial is the degree of that vertex in the hypergraph. So the problem reduces to finding the coefficient in this polynomial of the monomial that's got x1 to the d1 all the way up to xn to the dn, where d1 up to dn, of course, are the degrees you want to achieve. And now we pull out our elementary linear algebra and integrate each of these variables around a simple closed contour enclosing the origin. Remember, it's just a polynomial. The only singularity, once you've divided by some power of x, the only singularity is at the origin. So this formula is true for any contour enclosing the origin. That's just Cauchy's formula for coefficients. Now we'll find, we're almost going to find where the beta equations come into it. We'll take the contour for variable xj to be a circle, but there's a different radius for each of the variables. Xj's got a circle of radius e to the beta j, and it's got a new variable theta j telling you how far around the circle you've gone. So you make this substitution and you simplify and simplify, and you finally comes down to, there it is, finally comes down to some stuff at the front that doesn't depend on theta times a n-dimensional integral around circle, so minus pi to pi, of some function f of theta d theta. And the stuff in front of the integral is starts off pretty messy, but then you use the beta equations to simplify it, and it's just a nice product of lambda w to the minus lambda w and 1 minus lambda w to 1 minus lambda w. So here again, at the top is the answer, the number of hypergraphs as an integral. And the function that we want to integrate looks like that. And so we have to start analyzing this function. First thing to note is that this factor in the numerator there's a product over all R sets. It's a very large number of terms. And this factor, 1 plus lambda w times e to the something minus 1, because lambda's in between, lambda w is between 0 and 1, this factor is always at most 1 in absolute value, and it's only equal to 1 if the sum of theta j over j in w is a multiple of 2 pi, so that this exponential minus 1 is equal to 0. And putting that together for every factor, for every w, you find that there's exactly r points of concentration. So the integrand is always less than or equal to 1 in absolute value, and it's got equality if and only if theta is one of r points, and these points are when all the thetas are equal to some r submultiple of 2 pi. So 2 pi, there's one at the origin, and there's one where everything is 2 pi over r, and then so on like that around the circle, evenly spaced around the circle. But the thetas are not allowed to be independently at those r points. They have to all be at the same one. So this gives you r points of concentration in n-dimensional space. All of them happen to be equivalent because of obvious symmetries in the integrand. So we can just, to start with, we can just look at one of them. And as always happens in these problems, most of the contribution to the integral comes from close to these points of maximum value. So what does close to the point of maximum value? Remember, one of these concentration points is the origin, so we'll use that one. We'll define a thing called u of t. This is a box aligned with the origin centered at the origin, and it's got side 2t in every direction. And then that's not quite good enough because if we go to particular corners of this box, the integrand starts to have wild behavior, and it proved necessary to chop off some corners. So we'll chop off the corners where the thetas are all much the same. So where the sum of absolute value of the sum of the thetas becomes too large, we'll chop it off. So that's the intersection of a cuboid and the region between two parallel planes. So now we have to find the integral of our messy integrand inside this messy region. Fortunately, we have a general method which was proved by myself and Misha Isayev a couple of years ago. And I'll explain how this method is applied. Firstly, we have to define a matrix. It's a matrix A, and for the diagonal entries, you sum lambda W times 1 minus lambda W over all the W's that contain J, and that gives you the AJJ diagonal entry. And for the off diagonal, for the JK off diagonal entry, you sum the same thing over all W's that contain both J and K. Of course, these lambda W's depend on betas, so this is a bit of a obscure thing, but that's the definition of A. Now you expand using Taylor's theorem, expand the integrand inside this small region, and you find it looks like this. Firstly, you got a quadratic form, and A is the matrix of their quadratic form. Then you've got a function f of theta is a polynomial. It's got terms of degree 3 and 4 in it with complex coefficients. And then you've got something I call tiny, which is basically the remainder in Taylor's theorem, and it's small. Now, the first term's got terms of order 2 because it's a quadratic form, and the next one's got terms of order 3 and 4. What happened to the terms of order 1, the linear terms? Well, it turns out that the beta equations are exactly what happens. You have to solve. Remember, the betas determine the radii of the contours, and the beta equations are exactly what you need in order to make the linear terms in the integrand go away. So basically, that's why we used them. Okay. So now we've got this thing here, we've got a small region R, and we want to evaluate this integral looking like that. And what does the general method require? Well, firstly, you need a matrix T that diagonalizes the quadratic form. And it also has the property that the inverse maps the region onto remember these U's make cuboids aligned with the origin. So it maps the region onto something that contains a suitable cuboid and is contained in a suitable region, cuboid. And these row 1 and row 2 have got some requirements that I'm not going to state. And you also need some bounds on the norm, the 1 norm and the infinity norm of the matrix T. Now, in the past, this method or methods similar to this has been used a couple of dozen times in the past. But always we had to find T explicitly, and it's really quite hard for a problem that's irregular to find a sufficiently accurate estimate for T. But the beauty of our new method is we don't have to find T, we just have to prove that there exists a T that satisfies our requirements, because the answer doesn't have a T in it. And as well as this, we have to find some bounds on the first and second derivatives of the function f. Now, let x be the n-dimensional normal random variable whose density is proportional to e to the minus x transpose ax. So this is the normal distribution for whose density has the same quadratic form as our integrand. It doesn't have the other stuff, just the quadratic form. And then the theorem says that with some error term that we give, the value of the integral is pi to the n on 2, the inverse 1/2 of the determinant of the quadratic form times this exponential here. And this blackboard bold E means expectation. So x is a random variable, so f of x is a random variable, and expectation of f plus half of a thing that looks like the variance, except it's not the variance because it's a complex random variable. So it's actually the pseudo variance, if you want to be fussy about terminology. Now, the values of these expectations and pseudo variance can be bounded, or if you need to, estimated using a theorem of Isserles, also called Wick's formula, that tells you the moments of a multidimensional normal distribution. And in our case, we just turns out that under our conditions, these are small, both of these are small. So then the theorem tells us that the value of this integral is just within some error term, pi to the n on 2 times the determinant to the minus 1/2. So this gave us the integral inside the small regions at the origin. Remember, there's r of these equivalent regions altogether, so you just multiply this by r to do all of them. And now you have to get the contribution from outside these regions. And the next thing we did was we surrounded each of these r points of concentration by a box of size r to the minus 1. R is the edge size again, remember? And then inside those boxes, but outside these little regions, we divide into small parts, and we use the matrix T, again, just using the properties of T without knowing what it is precisely. We can use the matrix T to bound the function in each of those and therefore bound the integral. So now we've got the integral inside each of these boxes of size r minus 1. And then outside outside those boxes, which we now have the region where there's no point of concentration, contains all of the thetas within r minus 1. They can be distributed all around the place, or they can be concentrated some way away from a concentration point. And we have a couple of cases considered separately, basically according to whether they're clustered or not. And we bound the integral there. So overall, it turns out the integral outside the R small regions is negligible compared to the integral inside those regions. And it's what the answer looks like. Notice here there's a couple of things that depend on solving the beta equations. The matrix A depends on the beta equations, and you have to get its determinant. And each of these lambda W's is a function of the betas, so you have to do that. Okay, so all of this depends on beta. In that sense, it's not a nice theorem. It's sort of implicit. We have to tell the reader, go and solve the equations first, and then when you've solved them, put the answer in this formula and it'll tell you the answer. Slightly unsatisfactory, but that's what the answer is, so we can't help it. On the other hand, if our degree sequence is not too far away from regular, it is possible to solve the beta equations to sufficient accuracy to give an explicit answer. And let's look at that now. So how far away do we want from regular do we want to allow? Well, we want to allow any degree sequence which is reasonably likely to occur for a random hypergraph, because our aim was to study the degree sequences of random hypergraphs. So what we want is an explicit formula for any degree sequence that's likely to occur. And what happens for a random hypergraph is the degrees vary from each other by about the square root of d times log n. So if we set our limit of variation to be a power of d that's a little bit more than d to the 1/2, we will capture all interesting degree sequences. And we set our limit to d to the 3/5. So our conditions are, again, we're in the first quadrant. These are the same conditions I told you before. And delta max is big O of d to the 3/5. And delta j is the difference between dj and the average degree. Delta max is the maximum of those. Now remember what lambda is. It's what fraction of the complete graph you got. It's the average degree divided by the degree of the complete graph. And first of all, we want to find a good approximation for beta. And we did that by using an iteration. We started off with a value for the regular case, and then we applied the iteration about 4 or 5 times. Because we've got some bounds on the Jacobian of the beta equations, we know when we're close enough to the solution. We can put an explicit error term on the solution, and the solution looks like this. The first term is what you get if it's regular of degree d, and then you get another term, and there's another 4 or 5 terms there and an error term. So now we've got the betas, we have to substitute them in the other places. You have to evaluate the quantities in the expression for the number of hypergraphs. And the answer, I tell you, R sub t of d is the sum of the teeth powers of delta j. So this is the teeth central moment of the degree sequence. And A0 is like the matrix A, but it's just for the regular case. So we can write it down quite explicitly, and we can find its determinant quite explicitly, rather simple rational function. And then in the first quadrant, the number of hypergraphs looks like this. So now beta's gone away entirely. Everything here is quite explicit. You can work out these R2, R3, and R4 just from the degree sequence and substitute it in. And that gives you the number of hypergraphs. So now let's move to the problem we started with. What about a random hypergraph? We've got the number of them. So what can we say about the distribution of the degree sequence? Okay, so let's define some probability spaces. Firstly, D sub R of n and m is the probability space of degree sequences of random R uniform hypergraphs with n vertices and m edges. That's what we want to find. Another simpler probability space is, suppose you take some independent binomial variables with parameters n-1, choose r-1 and p, and then you condition those on having the correct sum. So the degree sequence sums up to r times m, because there's m edges and each one has got size r. So you condition your sequence of independent binomial variables on having the correct sum. It turns out the p's all cancel out, so this distribution doesn't depend on what p is. Kamchek, Liebenow, and Wormald, under their conditions, proved this relationship between the hypergraph degrees and the binomial model. And you can see it's got this large thing, r minus 1 over 2 inside exponential. So when r becomes very large, this becomes quite large, and the probabilities in these two spaces differ a lot. We proved a similar theorem. Instead of r minus 1 over 2, we've replaced it by this term in the front. And this is not a contradiction because these two theorems have got different conditions. And where the conditions overlap, especially when the edge sizes are small, when the edge size is small, when the conditions overlap, these two theorems agree with each other. So when the edge size is large, as we've seen, the binomial model doesn't agree too much with the hypergraphs. And Kamchev, Limanau, and Wormold suggested using hypergeometric distribution instead of binomial distribution. And the reason is very clear. If you take a random hypergraph and you look at just one vertex degree, say D1 degree of vertex 1, then the distribution of that degree is in fact a hypergeometric random variable. And the probability of D1 equals K is this messy thing that I've written there. Hypergeometric distribution is not terribly easy to work with. In fact, it's a bit of a nightmare until you come across a very nice theorem, which I'll mention even though we're not going to use it in the talk. The probability generating function for this distribution, so that's the power series whose coefficients are the probabilities, is a hypergeometric function. It's a 2f1 type of hypergeometric function. It can be written in some different ways, but it can't be simplified in terms of elementary functions. However, Vatutin and Mikhailov proved that this function, it's actually a polynomial in this case because of the arguments being integers. They proved that all the zeros of this polynomial are real and negative. And this means that it can be factored into linear factors that look like this, pj times x plus 1 minus pj, where every pj is between 0 and 1. And this is exactly the probability generating function of the sum of m independent Bernoulli random variables. So a Bernoulli random variable is one that's just 0 with probability 1 minus pj and 1 with probability pj. Now, exactly what these pj's are, nobody seems to know. They can be all mixed values. They just happen to be the zeros of this probability generating function. But once you've got a sum of independent Bernoulli random variables, there's a huge literature to draw on. Things like very nice and accurate tail bounds and local limit theorems that enable you to do things that are quite difficult to do if you're working with the original hypergeometric distribution. Anyway, we made good use of that in our proofs. And let's go now. This might be the last slide. So let's take n of these hypergeometric variables with the parameters that correspond to the degree of one vertex. Independent of each other. They're all the same and they're independent of each other, but then we condition them on having the required sum r times m. Then we prove that the degree, the probability of a given degree for hypergraph is equal to the probability of a given degree for the hypergeometric model. This is now the hypergeometric model times this expression here. It doesn't look much better than it did before for the binomials until you realize that there's no r in the denominator. Previously, that 1 was an r minus 1. And previously, this r2, r sub 2 here was multiplied by r. So this argument of this exponential is far more moderately changing when the size of the edge increases. And that's why this model is much better than the other one. And we can do a little bit more. If you consider the value of R2, so R2 is the variance of the degrees. Is that right? Yeah, I guess it's the sum of the delta J squareds, and delta J is the dj minus d. And you can find that for a random hypergraph, the value of R2 is strongly concentrated at a particular value. And it happens to be precisely that value that makes this expression inside the exponential close to 0. So what this shows is that except for a set of very small probability, and very small here is n to the minus omega of log n, except on that very small set, the binomial, the hypergraph degree sequence matches the hypergeometric model of the degree sequence to within a small error. And Kamchev, Liebenau, and Wormald conjectured this holds for all reasonable parameters. Of course, we only proved it for our parameter set, but that's quite a large parameter set. And I think that's the end, except thank you for inviting me and thank you for attending.
Thanks a lot, Brendan, for your very interesting talk. Are there any questions? So, Brendan, do you have any any approach for the Ds that deviate more, so to say, from the uniform kind of distribution? Is it like a realistic problem?
Yeah, so the last part of the talk about the random hypergraphs used a comparatively small amount of deviation, where the average degree is d and the deviation is d to the 3 on 5, sorry. But in the earlier theorem, we have a much larger deviation.
Yeah.
And we are not sure if there is, in fact, a theorem for a larger deviation. Here we got this 1 on R here.
Mm-hmm.
I would like to think that it's true when this is at most some sufficiently small constant.
Okay.
But our method doesn't work in several different places in that case. So it's work for the future. It might be true, it might not. I actually don't know.
Okay, but it might be the same formula, kind of.
There might be more terms.
Mm-hmm.
But again, I don't know.
Okay.
Yeah, because some of the error terms we used along the way to getting the answer I presented use this bound 1 on R. And if we don't have it anymore, there might be some terms that escape being suppressed.
Are there any other questions? Okay, so if not, well, thanks a lot, Brendan, and I really hope to host you in Moscow physically in some near future, maybe next year.
I hope so too.
Yeah, great, and see everybody in an hour on the talk of all the science. Bye, Brendan.